grateful for the organizers for not putting a finishing time on my talk. I was this gives me my opportunity to give my first 3-hour talk. So in second thought, decided it would be nice to have future talks with a non-empty audience. So I'll give a shorter talk, but probably still over 30 minutes. But I've always been fascinated my whole mathematical career with generating functions. So I'm going to give some examples of what I like about them. Two generating functions that have had a big influence on me, and 3 more that I discovered myself that are really cool.
You want to press down?
Yeah. Okay. So these are the 2 generating functions that I think have been most influential. People recognize it, 1 over 2 minus e to the x, and product 1 minus x again minus n. Explain more. I noticed very early as a high school student, I was aware of this first generating function for a number fn of ordered set partitions of 1 up to n. This number is also called the Fubini number. Generating function due to Cayley and Whitworth, who had an factorial down here. It's an exponential generating function, 1 over 2 minus e to the x. Then I'm taking a course in number theory from Postel when I was an undergraduate. I ran across this theorem of Kalmar. Gn is the number of ordered factorizations of the positive integer n, the number of ways of writing n as a product of integers greater than 1, where you take order into account. The Dirichlet series generating function is 1 over 2 minus zeta. So as a college student, I knew, as undergraduate, I knew both of these results. I knew there must be some connection. Didn't know what to do about this. I didn't think anyone would be interested in either. And finally, I realized another result that fits into this picture is if C of n is the number of compositions of n, the number of ways of writing n as the sum of positive integers when you take order into account. Everyone knows this is 2 to the n minus 1. Then the generating function can be written in the form 1 over 2 minus 1 over 1 minus x. So I also realized senior year, first year of graduate school, that these things have interpretation, these numbers have interpretations in terms of chains and posets. Very obvious, easy to see this. F of n, the number of ordered set partitions of the known set, is just a number of chains in Boolean algebra, Dn. Differences in these sets for ordered set partition. And Gn, the number of ordered factorizations of n, is the number of chains from 1 to n in the lattice of divisors of n. And Cn, the number of compositions of n, is the number of chains 0 to n, the chain of 0 to n. So this was sort of the motivation for much of my further work on generating. I'm not going to go into the details of how I then developed this. You can see these facts suggest many questions which led to many other interesting developments. Oops. Now, it turned out that more recently, the generating function for ordered set partitions is 1/2 minus e to the x came up. This has to do with math overflow. Someone mentioned that I contribute to. So this application is not great mathematical significance, but it does involve two very famous field metal lists. And here it is. One of them, the first one is Tim Gallagher. So I hope everybody can read this, although the details are not that important. But this is a question he proposed 13 years and 10 months ago. Says, how many stirred sections are there from set of size n? And well, this S of nn is a Stirling number of the second time, the number of partitions of an element set in n blocks. And basically, in his update, he said that he's really interested in the sum of m factorial S of nn. So m factorial times S of nn is the number of ordered set partitions in an element set into m blocks. So if you sum all n, you just get the total number. Set partitions in an element set, which is the Rubinian number. And he suggests, he doesn't know any of this, he suggests that one way of tackling this problem is to look at sum of m factorial S of nn to find the value of m that maximizes the term m factorial S of nn. That'll be approximately asymptotic, to the number. The largest term will be approximately the sum, which is very few terms compared to the sum. So here's my reply. I pointed out that, well, for one thing, the actual generating function that he was interested in, P of nx is, we look at this polynomial S of nm, x to the m. So he's interested, should be an m factorial, well, we have this polynomial, P of nx, m factorial S of nm, x to the m. He's interested in the value, Gallagher's interested in the value of x equals 1. And, but, he also raised the question of which value of m achieves the maximum term. And I point out this amazing theorem of Tharoff that if this, well, in general, if you have a polynomial with positive coefficients and real zeros, then the exponent, the term that the largest term, the mode, is within 1. Pn prime of 1, Pn. So we could try to apply it to Gallagher's question. So the generating function for this Pn of x, simple, generating exponential generating functions is this generating function here, 1/1 minus x e to the t minus 1. He's interested in the value where x is 1, which is 1/2 minus e to the t. This the generating function for ordered set partitions. Derivative generating function, you just have to differentiate this with respect to x, set x equal to 1, to get this. And so if we could prove that this polynomial had real zeros, we would be able to try to estimate this Pn prime of 1 over Pn of 1 using Tharoff's theorem. And a little after that, updated this reply with a simple transformation that with words having real zeros that converts Pn of x to the Riemannian polynomial, don't they have real zeros? So indeed, Pn of x does have real zeros, and we can apply Tharoff's theorem. So Gower's response, I'd like, thanks for this. It makes me realize that I need a more developed break down the generating function reflex together with some knowledge about how to deal with it once it's written. Okay, so like the first famous mathematician involved in this. Then Harry Howard has a picture about figuring out the asymptotics of this f of n and this p n p prime of n at 1 divided by p n of 1, and he said that you could do this. Principle, this is an exercise in a saddle point method, one which does require a non-trivial amount of effort. So I point out that you don't need a saddle point method for this kind of generating function with these isolated singularities. There's a very simple general technique. I even taught it when I was taught a service course in the graduates. So I do it for this generating function p n prime of 1. Do a simple computation of this as a compute, really the first term of some one series. And finally, you get this ratio of asymptotic of n over 2 log 2. So that's the asymptotic, the value of m maximizes the number of ordered partitions of n element set, n blocks, n over 2 log 2. But what's really cool about this is the response of tau. I didn't realize it was so simple to read off asymptotics of the Taylor series from nearby singularities, though in retrospect, I implicitly knew this in several contexts. Thanks, I learned something today. Very, very gracious. Okay, now, I was discussing the similarity between these generating functions, 1 over 2 minus e to the x, 1 over 2 minus zeta of s, and 1 over 1 minus x. So fairly recently, I became aware of a similar phenomenon. So look at these 3 facts. F of n is the number of partitions of n, such that no part appears exactly once. So this generating function for f of n, I think was known to Big Bang. Notice this is 1 minus x to the 6k, 2k, 1 minus x to 3k. Let f of n be the number of monic polynomials of degree n over fq, such that no irreducible factor has multiplicity 1. Okay, so here we get this generating function. X to the 6, x squared, x to there's kind of something. Which just can't be a coincidence. And also let S be the set of all powerful positive integers. The positive integer is powerful if whenever a prime divides n, then it's squared. And if you look at the Geological series, the sum over all powerful numbers, 1 over n to the s, is negative 2s, negative 2s. So recently I worked out generalized explanation for all of this, and I won't take the time to go into it here, but it's on my webpage. I posted on. Now, so that is what I wanted to say about this generating function, 1 over 2 minus e to the x. And the second one, generating function had a lot of influence on me. Most of you are familiar with it, but I'll review the definition. A plane partition of n is this planar array, pi ij, ij greater or equal to 0, non-negative integers, weakly decreasing in rows and columns, and summing to n. PPN will be the number of plane partitions of n. So here are the 6 plane partitions of 3. Rows and columns are weekly decreasing, and there's infinitely many zeros completely erased, not all the way. So McMahon, what he conjectured in 1897, published a proof in 1912, this very famous generating function for plane partitions of a 1 over product of 1 minus x to the I. And for me, this was the gateway to many interesting further topics: symmetric function theory, RSK algorithm, theory of P partitions, common reciprocity was suggested by some of the stuff going on here, like especially with the theory of P partitions. So I won't say anything more about this, except that this generating function of McMahon really ended up having a big influence on.
Is there a good exposition of this anywhere, Richard?
So what I'll do now is discuss 3 generating functions of my own. That I would say the 3 favorite generating functions I've discovered. And here's what they look like, just the generating functions. So there are 2 things I like about them. First of all, they're kind of exotic and mysterious looking, strange looking things. That how could they ever appear in some of these combinatorial problems I'm going to mention? And the second thing I like about them is the only way I know of proving these results, which I've been down yet, but which these are the answers, is using mathematics from other branches of the combinatorial. So I don't know how to prove these results without reading combinatorics. But with this middle one, well, I'll explain later exactly what this means. So these are the other branches of mathematics that are involved in obtaining these generating functions. Gerhardt theory, the isomotopes, representation theory of the symmetrical, theory of paper plane arrangements. So the first problem is to count ordered degree sequences of graphs. So G will be a simple graph on vertex set 1 up to n. No loops and edges. The degree I mean the degree, the number of adjacent vertices with vertex I. D of G will be the nth degree of vertex 1 up to the degree of vertex n. Ordered degree sequence of G. Now, traditionally, when people talk about degree sequences, they sort the DG, decreasing point, and they call it the degree sequence. And actually, it's still unknown any kind of reasonable formula for the number of distinct degree sequences, graphs on 1 up to n. Even getting good estimates is highly not trivial. But for ordered degree sequences, we can't count how many there are for graphs and vertices. So what's the f of n be the number of distinct ordered degree sequences of graphs and vertices? So for a graph with 3 or fewer vertices, 2 different graphs have different ordered degree sequences. So there's 2 to the n choose 2 graphs on vertex set 1 up to n. All of them have distinct ordered degree sequences. But when we get up to 4 vertices, there's 54 distinct sequences. For instance, there's 3 different complete matches for vertex set, and they will have the same ordered degree sequence, 1, 1, 1. So it's less than 64. So here's this mysterious generating function I obtained for f of n. I got involved, n to the n minus one, to the n minus one, n to the n minus two. So, where did this come from? I mean, you see all these n to the n type things that suggest trees and somehow be involved. There's no trees in the original formulation. Well, I should also say, in case you're curious about the asymptotics of f of n, cuts of n, obtained from this asymptotic formula, some constant n to the n minus. Well, the secret of obtaining this is an intermediate result. This lemma that expresses this number f of n in terms of something else that can be counted by manipulatorcs. So, this manipulatorcs, so I really like this term, if you want to see it. Just, manipulating results. No real idea. So here is the key lemma. The f of n is the sum of all simple graphs that went up to n, such that every connected component has at most one cycle. That cycle has, if it exists, it has an odd length. And C of G is the number of these cycles. Sum over all such graphs, the maximum 1 and 2 to the C of G. So I said, so once you have this, you can find the generated function manipulatorcs. But how do we obtain this lemma? We have to connect it with the theory of zonotypes. F of n is the number of integer points in a certain zonotype. The zonotype is a Minkowski sum line segments. Namely, the line segments connect the origin to all vectors ei plus ej, where I less than j, where ei is the ith unit coordinate vector. And this is a polytope of degree sequences that was considered before by Perlis. And you can also, ask other questions, whether it's vertices, etc. I think in the same paper where I computed f of n, I worked out the f vector of this zonotope. And it's quite easy to see that f of n is the number of integer points inside the zonotope. Then you just use this formula for the number of integer points. It's a sum of absolute values of determinants. So pretty long, hairy computation, but still straightforward in some sense. Finally, get this combinatorial interpretation. Basically, you have to take this matrix, n rows and n choose 2 columns. There's 2 1s in every row, all possible n choose 2 ways. You have to be able to determine all the line. So that was the secret to proving some. Asked if there's a combinatorial, direct combinatorial proof of the lemma. Number of degree sequences is given. There's a similar result for degree sequences of formulas, which is somewhat simpler. That number is just the number of forests on n vertices, and that was in the combinatorial proof by Stanley and Winston. So we could try to do something now and see. Okay, so my second generating function that I really like arises from a theorem of bondage. So this is one of his notebooks, not his lost notebooks. Unlost notebooks. Namely, this is an analytic theorem. So as x goes to 0 from above, you look at this sum twice, n greater than equals 0, 1 minus x over 1 plus x, n plus 1, and he asked for the asymptotic behavior of this function. And it's not a formal result, you know, if you formally expand this out, every one of these terms has 1 as a constant term, so 1. Truly analytic result. If he computed the asymptotic expansion up to this term, it looked like this. Let's call this power series f of x. Now, Bruce Banham, I saw the work figured out a formula for the higher asymptotic series. So I remind you that where the number En is, the exponential generating function for where the numbers is secant x plus tangent x, and rephrasing Bruce's results. The days, first day of birthday conference, joint birthday conference, 85th birthday conference, Bruce parent, George Andrews, which explained what George Andrews is not here. But let's say E be capital E will be an indeterminate size, a linear operator that takes E to the n to the Euler number E. Like it's going to be a linear operator.
Sorry.
Polynomials in the E's or coefficients of power series and x. Gets rid of the E and just leaves you with the power series in x. That's rid of the n's. And so Barron's result is you look at you take the series 1 plus x over 1 minus x to the e squared plus 1 over 4. So you expand this out by the binomial theorem as the power series in x. The coefficients are going to be polynomials in the e's. And then you take each e to the n in these polynomials and replace it by en. So you're going to get a power series with integer coefficients, or at least with rational. You know, people with umbrella calculus will feel this is some kind of umbrella, standard umbrella operation. Bring down the exponents and subscripts. And Galloway, 1999, raised the question that we let little f of n be the coefficient of x to the n in this series. In other words, in this expression, find a combinatorial interpretation of n. And it's kind of remarkable that this had a nice simple answer. It showed that f of n is simply the number of fixed point free alternating involutions in the symmetric group S2n. So fixed point free involution, all the cycles have length 2. You know what an alternating permutation is? A1 greater than A2 less than A3. So the only way I know how to prove this result is to go through the representation theory of the symmetric group. In particular, we use this character originally due to Folks, some more general context. But there is some character, usable character of Sn, so that for all permutation W, the value of a character is either 0 plus or minus some real number. And then you start using all these known results to connect behavior characters of Sn for properties of computations. This result eventually works out. By the way, this character is just the skew character of or staircase version. Let's start the left one down. That's usually. So I'm wondering when if it makes sense to generalize this original question of Ramanujan. I don't know if this particular question makes any sense, but we could put in a couple of parameters here. You know, Ramanujan was looking at the case where A equals B equals 1 in this form. What if you generalize it this way? Will you get some kind of nice refinement of alternating fixed point solutions? I don't really know enough analysis to try to do this. And we should generalize many other, I mean, this 1 minus x over 1 plus ax can be placed with so many different things, maybe some of them be interesting company for us. Questions about? And my last generating function that I'm fond of is connected with interval orders. So suppose we have a set I1 up to IN, closed intervals of positive length, closed intervals in the real numbers. And we make them the elements of a coset P. We'll define ith interval II to be less than the jth interval. Capital I sub I lies entirely to the left of I sub j. So this is the interval order. That is actually labeled interval order because we have the subscripts and the odds label the points. So let's suppose we give them the length of these intervals. Li is the length of the ith interval. L will be the vector. And then the script I sub L is a set of all labeled interval orders with intervals of length L1. So, for example, we know if all the LIs are equal, and we're looking at unlabeled interval orders, that number is a Cadillac number. These are also known as semi-ordered. Unit interval orders. What about the labeled case of all the LIs are equal? Of course, usually except people want. Doesn't really matter what value. The number Fn of labeled interval orders with all the LIs equal. The exponential generating function is given by taking the generating function for the unlabeled case and substituting 1 minus e to the minus x. So I think again, John worked out a sort of a more general scenario where you go from the unlabeled to the labeled case by this substitution 1 minus e to the minus x. But that takes care of the labeled interval orders for the case all the intervals at the same length. But what I'm concerned with here is generic lengths. I want to give a precise definition of generic, but linearly independent over the brackets pretend to be generic. And let us let Cn be the number of labeled interval orders, size n, generic interval lengths. A priori, it's not clear that Cn only depends on n, not the actual lengths. It's kind of surprising. There's so many different ways these intervals can have lengths can be generic. You don't get the same interval orders of the isomorphism. A number of them will be the same. And we'll let the exponential generating function for Cn, we'll call it Z. Here are what the first few terms look like. 2, 19, 195, 7. So I show the following theorem 1998, let's define another generating function y, which again 1 plus x plus 5x squared over 2, etc. By the condition that y of 2 to the minus e xy equals 1. Then this z, this generating function for generic length interval, this unique power series satisfying z prime over z equals y squared, z of 0 equals 1. Seriously development. Where did this come from? Well, very super brief steps of proof is to show that Cn is the number of regions of a certain hyperplanar region. Right? Now, there's all kinds of formulas for counting the number of regions of a hyperplanar region, and you plug into one of those. A huge amount of work, visual torics, but finally. So I think there's a lot of interesting open problems connected with these labeled interval orders. Now, so suppose we have two sequences of lengths, L, M. We can say they're equivalent if you look at the sets of interval orders you can get from these lengths, and the elements of these sets are isomorphic to each other, then we can call the lengths equivalent. What are the equivalence classes? Well, even for generic lengths, I mentioned that over the number of labeled interval orders when the lengths are generic, it's always the same. The actual isomorphism classes are not. I mean, you can see this, for instance, super increasing of lengths. These are two examples. If the lengths increase very rapidly, power 2 is sufficient, and Li is 2 to the I. Then you can have a chain of length 3 incomparable with a single point, that is 3 plus 1. You're asking for 3 intervals, that don't overlap, and some other interval overlap all of them. And it's clear that we can do that very long lengths. But if we take the Li's generic almost equal in length, then you're not going to be able to get 3 plus 1. So what different kinds of isomorphism classes do you get? Particularly these two special cases seem worth looking at. And then we can ask about the unlabeled interval. When they all have the interval orders, all have the same length, and very nice connection between the unlabeled and labeled orders. I don't know anything about the unlabeled interval orders, the generic interval lengths. Yeah, I didn't really check. Even if the number of them depends only on n. Wouldn't be surprised if it did it. What can you say, especially in these two cases, super increasing and almost equal to this? Okay, oops, we should say this finishes the mathematics part of my talk. But I wanted to say a few additional words. I didn't have an opportunity to say anything at the banquet. I'm going to give a kind of condensed version of what I'm going to say later. So really, this has been such a great meeting. It's really wonderful to see so many people here, both familiar friends and new faces. It's the best way to distract me, thinking that in only 18 days, or now it's actually 16 days, my youth. But I'm not going to Well, this statement for the bank was really doesn't, it's not really applicable here, but on the other hand, rather disappointed to see so many mathematicians here. You should be at home in your offices studying math, not wasting your time on frivolities. And it's also nice to see such a wide range of career stages of the conference participants, beginning with graduate students and now even junior high school students, up to retired codgers like myself, both within and outside academia. And it goes without saying that I'm pleased that my two children, Kenneth and Sharon, are able to be here today. And I mentioned that this was also the first time that I heard Sharon getting talk. So there are some significant differences in my life in my previous birthday celebration, 70th birthday, my present one, beside the obvious age difference. Professionally, I am now retired from MIT and spent 3 semesters at the University of Miami. On a personal level, the main difference is the acquisition of my partner, Esco Kiba, who has been a big enhancement to my life. Another acquisition since the previous conference, my 2 grandsons, Bennett and Cole. A once in a lifetime situation currently exists with my son Kenneth, his 2 sons. Namely, their ages are all perfect squares. Not only that, the digits in the age of my son are the ages of my grandsons. So everybody can very quickly is able to. There's a 3 ages syndrome. So I'm looking forward to another great celebration 10 years from now, not only for the celebration per se, but also because it will mean that I'm still around. Being on the safe side, rather than having these events once a decade, it might be better to have them at least once a year.